Welcome to video 4.8 in our first Principles of Astrophotography series. In this video we discuss photoionization, which is the process of stripping electrons from an atom by capturing a photon.
Why is photoionization important?
It's important because without it, diffuse nebulae like the Orion Nebula and planetary nebulae like the Ring Nebula would be invisible.
That'd be awful. This video is based on section 4.8 of our first Principles of Astrophotography book, which is linked in the description below. I'm Ren Edwards.
And I'm Boyd Edwards.
Let's talk sensibility. Principle 69, photoionization. Photoionization is the process whereby an atom absorbs an ultraviolet photon that is sufficiently energetic to eject an electron.
So in a previous video, we talked about the fact that light can be thought of as both a wave and a particle. And when it behaves as a particle, the little packet of light is called a photon. And those photons carry the frequency and the wavelength of the light that they're part of. So if you shine your flashlight, it emits a photon of wavelength, emits light of wavelength 550 nanometers. The photons that it's emitting have that wavelength. So the photons carry the property of the wave-like thing. So what happens now in photoionization is that a photon that has an ultraviolet wavelength, we talked about the range of visible wavelengths being between 400 nanometers and 700 nanometers, and the wavelengths shorter than 400 nanometers are ultraviolet. And ultraviolet photons that are sufficiently energetic to eject an electron. So that's what photoionization is. The ultraviolet photon hits the atom, kicks an electron off of the atom, and that's what photoionization is. Clear enough? Yeah.
Clear as mud.
Yeah.
Principle 70, Emission nebula ionization. Diffuse and planetary nebulae are photoionized by one or more nearby hot stars, while supernova remnants are ionized by collisions of expanding supernova remnants with interstellar gas.
So we're going to talk more in the next video about this process, this collisional excitation, as it's called, in supernova remnants. Right now we're going to focus more on diffusion nebulae like the Orion Nebula and planetary nebulae like the Ring Nebula. And they are photoionized by one or more hot stars. So those stars are sending off energy into the gas and dust that surrounds them, and those ultraviolet photons that are part of that light ionize the gas, and that's how we can see it. So for example, in the Orion Nebula, right here near the middle is the trapezium. It's a little hard to see it. You can see it in an astrophotograph if you take a really short exposure. Most astrophotographs just completely overexpose the trapezium, including probably ours. Mm-hmm. And this one, it's a little hard to see. You might be able to see some of those stars, but those are very hot O and B stars that are sending out ultraviolet radiation that's ionizing the nebula.
Principle 71, Lyman limit. Photons of wavelength 91 nanometers or smaller have sufficient energy to ionize hydrogen and are called ionizing photons.
So just to recall from a previous video, we talked about the energy of the hydrogen atom being negative 13.6 eV. eV stands for electron volts. It's a very, very small measure of energy, not a measure of voltage, but of energy, divided by n squared, where n is the principal quantum number. N equals 1 gives the lowest orbit of the electron, then 2, then 3, and all the way up to infinity. So for n equals 1, the energy of that state is negative 13.6. As n goes to infinity, then you have 1 over infinity squared, which is a very small number, and the energy goes to 0. So the difference between the energy of the ground state, the n equals 1 state, and the ionized state is where n equals infinity is 13.6. So that's the energy difference that is required to ionize the atom. So then we also talked about the fact that a change in energy, that the energy of a photon is Planck's constant h times nu, the frequency of the photon. But we also know that c equals nu times lambda, where c is the speed of light, nu is the frequency of the photon, lambda is the wavelength of the photon. So if you solve that equation for nu, you have nu equals c over lambda, and then you substitute that into here, you get hc over lambda. Now this is important, that the energy emitted is inversely proportional to the wavelength. The energy of a photon is inversely proportional to the wavelength of that photon. So higher wavelengths mean lower energy, and lower wavelengths mean higher energy. And so if you work this out, if you take this energy of 13.6, put it in here, 13.6 eV, put it in there, you put in Planck's constant, 6.63 times 10 minus 34 joule seconds, and then we'll put that in here, put in the speed of light here, and you solve for the wavelength, then you get this so-called Lyman limit of the wavelength.
Okay.
So anytime you have a photon that has energy that's greater than 13.6, or a wavelength that's less than 91, then you're going to ionize that atom. So, and those, we call those ionizing photons. So this squiggly line is an ionizing photon.
Is this wavelength specific to hydrogen?
Yes. Yes, and also in the book, we do the same calculation for other atoms, like oxygen. What wavelengths do you need to ionize oxygen once, for singly ionized oxygen? What energies and wavelengths do you need to ionize doubly ionized oxygen? But they're all roughly around 100 nanometers or so, or maybe a little more, a little less. This just gives you a good idea about where you need to be wavelength-wise to ionize an atom. Great question. So this is an electron that gets ejected. And this is the proton of the hydrogen atom. So once you eject that electron, then what you have left over is just the nucleus of the hydrogen atom, which is a proton. Very, very sad, sitting there all on its own. Yeah, positively charged. So that's where this 91 is a very simple calculation to come up with that 91 nanometer Lyman limit.
It may be alone, but at least it's still positive.
Yes, it is still positive, and it has a positive outlook on life and everything, and it's lost the negative influence of the electron on
It's
it.
actually maybe not a bad thing.
It's not a bad thing.
Principle 72, thermal electron. Electrons ejected by photoionization acquire the excess kinetic energy from that process and are called thermal electrons.
So remember, the energy of the photon has to be greater than or equal to 13.6 eV, like we talked about in the last slide. The wavelength of the photon has to be less than or equal to 91. That's what that symbol means, a less than or equal to 91 nanometers. So if, for example, the energy is 20 eV, and the wavelength is whatever it turns out to be, 40 nanometers or something like that, then where does the extra energy go? Well, first of all, let's ask the question, what happens if a photon comes in that's exactly 91 nanometers in wavelength, hits the hydrogen atom? That energy is enough to strip the electron off the atom, but that uses up all the energy of the photon. And so that electron is just kind of sitting there looking down at the poor proton saying, hi.
Positive
But
proton.
he's still hanging out. The electron's still hanging out, doesn't have any energy. But if I zap it with a more energetic photon, then after you use up that energy of 13.6, then the extra energy is going to go into the electron, and that will become really important later when you talk about collisions. So those electrons that are ejected are called thermal electrons.
Is it because they're coming in hot?
Yeah, or leaving hot.
Leaving hot,
Yeah,
right.
Yeah, photons coming in hot. Thanks, Rand. I appreciate that.
You're welcome. Principle 73, ionizing photon production. Stars of temperature 30,000 Kelvin emit 1 trillion times more ionizing photons than the sun, mainly because of the shift towards shorter wavelengths of the blackbody spectrum with increasing temperature.
So in a previous video, we talked about the blackbody spectrum of stars. The star A here is Betelgeuse, and it has a temperature around 3600 Kelvin. This is replicating our sun. This, I believe, is replicating Rigel. But the bottom line is that as you get a higher and higher temperature of stars, the peak in the radiation that it sends out, the peak wavelength gets smaller and smaller. So this star A, which has a temperature of about 3600 degrees, has a peak wavelength of 800. Well, 800 nanometers is beyond the visible range. It's in the infrared range. And then this star B, which I believe is the sun, has a peak wavelength at around 500 or so. And then star C has a peak wavelength of around 200 nanometers. Star D is a star of temperature 30,000 degrees. And I did this one, I put this one in this graph specifically so we can think about these stars of temperature 30,000 degrees. So as you can see, this peak in this blackbody spectrum for this very, very hot star occurs pretty much right at the Lyman limit, which is 91 nanometers. And you'll notice that this vertical scale here is logarithmic. So compared with this 3600 degree star, this 30,000 degree star has 10 to the fifth. That's 100,000 times more energy at its peak than the 3600 degree star. So that sends more energy into the ultraviolet ionizing area. And I know we had a conversation with Nadine's family, or with Reynolds' family about this, and we talked about the sun has a temperature of 5,800 Kelvin. That's about 6,000, right? And comparing 6,000 to 30,000, you just have to multiply this number by 5. 6 times 5 is 30. And you get that stars of temperature 30,000. So you might expect that you get about 5 times the number of ionizing photons. But you might be wrong.
Yeah.
What you end up with is 1 trillion times more ionizing photons than the sun. So the sun does send out some ionizing photons, and if we have gas and dust in the vicinity, it will ionize it, but there just aren't very many of them. And it just isn't really enough. What else do I want to say about that? We go into a fair amount of detail on this calculation to come up with that 1 trillion times number. It involves an integral that you have to compute numerically. Anyway, if you're interested in the details, see our book. And thanks so much for watching.
And we'll see you next time.